Okay, welcome back. Last time we looked into an example for information measure. Basically, we have example to compare such as the shower entropy and the conditional entropy, mutual information, and conditional mutual information, and so on. And today I want to show some of these properties of this information measure. Basically, I want to show that all of them has to be bigger than or equal to 0. And I also want to show some of the upper bound for these quantities. And before I get started, I want to introduce one more quantity that I mentioned last time at the end also. There's the relative entropy, or the Kuiper-Leibler divergence. It's a measure, or you can think of a measure, between two distributions, let's say Px and Qx. So you can think of like when Px and Qx are identical, then basically D will be equal to 0. Otherwise, Px and D, Px, Qx will be bigger than or equal to 0. And I also mentioned that this is not a real measure in the sense it's not commutative. In general, I don't have dpx qx is equal to dqx px. So note that, by the way, this measure is over two distributions. So I have written this px qx. Sometimes you just use shorthand notation, just dpq like this. And this dpx qx is defined as sum over px log px over qx. So I want to show this is bigger than or equal to 0. Basically, I will use a very simple inequality. I'll use an inequality that's consider log x is basically something like this, right? This is log x. And log x is less than or equal to 1 minus x. And this is 1 minus x. Oh, sorry, it should be x minus 1. Okay, one can very easy to verify this inequality. Basically, this will only, log x will only equal to x minus 1 when x is equal to 1 at this point here. And we can show that the slope at x equal to 1 is basically equal to 1. Is kind of this, therefore this y equal to x plus 1 will be tangential to this curve like y equal to log x here. And also we can easily show that this is concave. Convex. Concave, I'm sorry. This is concave. Therefore, like this will be bigger than this, just as shown here. So, okay, by this inequality here, I can just rewrite this as sum over xpx minus log qx over px. Basically, I flip the numerator and denominator, and then I put a minus sign in front of it. And this is equal to, this is bigger than or equal to, so note because log x is less than or equal to x minus 1. Oh, by the way, this is like log 2, this is lateral log, but it doesn't matter. We know that like log 2 something is just equal to log 2a is just equal to lateral log a over lateral log 2. So therefore I have this log log 2 this thing is equal to lateral log qx over px. Put a minus here also. Over log 2 here. So that is px. And again, this log x is less than or equal to x minus 1. Therefore, minus log x is bigger than or equal to minus x minus 1, or like 1 minus x. So therefore, this thing here is bigger than or equal to 1 minus qx over px. Oh, sorry, this should be equal sign here. And this is bigger than or equal to px 1 minus qx over px. Then of course I can just multiply px into this, and then I have x sum over px minus sum over x sum over qx over x over log 2 should be equal here. And because px and qx are both distribution, so this will sum over to 1 and sum over to 1. Therefore 1 minus 1 will get cancelled, and therefore it will be equal to 0. So okay, what I just show is that the Colbert level divergence, or is also known as the relative entropy, and basically the relative entropy between P and Q is always equal to or bigger than or equal to 0. And we see that like this holds as an equality only when this minus log qx over px is equal to 1 minus qx over px. And we know that this equality only holds at the points that this is equal to 1 or qx over px equal to 1. That means that basically we have these two distribution is identical. So therefore we have this is always bigger than or equal to 0, and p dpq is equal to 0 if and only if px is equal to qx. So okay, I guess I can erase some part of it. I don't need this anymore. Okay, so now what we can see is that we can relate the mutual information or express the mutual information by the relative entropy. Basically, the mutual information I xy is just equal to hx minus hx given y. Alright, this is by definition. And what is the tricks is basically px log px minus and plus here y py x px given y log px given y, right? And here I can just, of course this basically is just pxy here. These two can combine. Py multiplied by px given y is just pxy. I can just write like this here. And px basically can think of equal to, it's the marginal distribution of pxy, right? So we can just marginalize the joint distribution pxy over y, then we get px here. So therefore, this is really equal to px. So I have sum over x here, log px here. So therefore this pxy can pull out, not pull out, but I can share a common factor here. I can just factoring this out and have log px plus, sorry, it should be minus now, and minus log px given y. Or maybe I can put the minus sign here, the plus and minus here. So therefore I have like sum over xy p xy log p x given y over px. And by base rule, I know that p x given y is equal to p xy over py. So therefore this will be just equal to pxy over py. So this is basically another way to write the mutual information between x and y. But if you compare this with the Kuiper-Leibler divergence, basically you can see that now the only difference is that this pxy is like the px here, and this pxpy is like the qx here. Therefore, like ixy can be represented as, using the relative entropy or the tail divergence, as p dpxy pxpy. So we have already shown that the Kuiper-Leibler divergence is always bigger than equal to 0. So this shows that mutual information has to be always bigger than equal to 0. And what's more is that this is equal to 0 only when this pxy is equal to pxpy. So there's ixy is equal to 0 if and only if pxy is equal to pxpy. But that's exactly the definition to be like x and y are independent, right? So this is exactly what we expected. Like the mutual information between x and y will be equal to 0 if and only if x and y are independent. And let's see. Given ixy is bigger than equal to 0, and we immediately have another inequality. Let's say we have ixy is bigger than equal to 0, and ixy on the other hand is equal to hx minus hx given y. So therefore, like hx, we have hx is bigger than equal to hx given y. And this is kind of obvious also, like if you are having, basically sometimes we call this inequality as conditioning reduces entropy. Basically, every time you know something more, the amount of remaining information should be less, right? So when if I doesn't know y, I will know, the amount of remaining information, that's hx, will be bigger than when I know y, there's the amount of information is just given y here. So, and another thing I can immediately get from this inequality is that know that hx is really equal to ixx, because ixx is equal to hx minus hx given x. I'm knowing x, that x is just a constant, therefore this has no information. This is equal to 0, so ixx is just equal to hx. And we know ixx has to be bigger than equal to 0 because all mutual information is bigger than equal to 0. So therefore hx is bigger than equal to 0 also. And let's see what else. I actually can easily show another bound for hx. So we have a upper bound for hx given y, and apparently I will have hx given y is bigger than equal to 0 also, because hx given y is nothing but the expectation of hx given small y over a distribution of y. So each of these is just, you can think of just a normal Shannon entropy, but parameterized by a parameter y here. And of course this has to be bigger than equal to 0, as we just shown here. And py has to be bigger than equal to 0, therefore the multiple bigger than equal to 0, the sum of all the positive numbers will be bigger than equal to 0. Therefore, hx given y in general will be bigger than equal to 0 also. So let's see summarize what we have for the moment. We have hx given y is bigger than equal to 0 less than hx. Ixy is bigger than equal to 0. Hx is bigger than equal to 0. And this apparently is bigger than equal to 0 also, because Ixy given z also is, you can think of an average over Ixy given small z over a distribution of z. This is Ixy given z. And again, this is just a normal mutual information you can think of, and is parameterized just by some small z here. So all of this has to be bigger than equal to 0, and PAC bigger than equal to 0. Therefore, Ixy given z is bigger than equal to 0. And I want to get a bound for hx. I have a bound for Ixy can be just hx and hy, right? It's smaller than both hx and hy, because Ixy is basically equal to hx minus hx given y, and hx given y is bigger than equal to 0. So therefore, Ixy has to be less than equal to hx. And similarly, it has to be less than equal to hy also. And for hx, what I can show is that it will be bounded by the log of the continuity of the size of the set of x. Let's see how I can show that. So hx, let's think of it has x can take some value like a, b, c, d, e, and so on, lots of, and can take the alphabet size, let's say, is absolute of x denote as. And let's think of a uniform distribution 1 over small x. So all of these have the same probability 1 over this 1 over the number of characters. And if we think of let's look at this thing here. For, let's say the original distribution is px. So let's try this. Let's see what we have here. I know this has to be bigger than equal to 0, and this is equal to 1 over x log Actually, this is a bad one. I guess maybe I should flip it. Let's see if I can. Let's consider this px 1 over x. So this I get, this is equal to px log px, so yeah, over 1 over x. Right, that's the Cooper-Leibler divergence. That's equal to that, sum of x here. And then this will be just equal to px log px plus sum over px log 1 over x, or I can write minus log x here, sum over x. I know this guy has to be bigger than equal to 0. This is bigger than equal to 0. And this is just equal to minus hx. So I can flip this hx on the other side. And I guess I flipped the sign somewhere. Yes, that should be plus. This is minus 1 over log 1 over x here, because this p is over 1 over x. So it's minus log 1 over x here. And then if I flip this sign here to log x, I have a plus sign here. So okay, everything is right. So this log x is just a constant. Okay, this is the size of the alphabet. It's a constant over x. I can pull this log x out. Then I only summing over this px is, of course, it's just equal to 1. So therefore I will have a log x is less than equal to bigger than equal to hx. So I have basically hx is less than equal to the log the alphabet size. And of course I get this when everything is uniformly distributed. So to summarize, I have this inequality here, but of course I can put one more here. Let's say this is less than equal to h given z and hy given z and so on. By the way, like you see that like I have an inequality here that hx given y is less than equal to hx. So a lateral question that some like first time to see this thing probably will arise is like, how about if I compare ixy and ixy given z? Do I have ixy is bigger than equal to ixy given z? So I guess I will leave this open until the next segment.